Problem 6.55 is a one-dimensional problem in which we try to calculate the amount of work it takes to stretch a rubber band. This rubber band has an unstretched length of L0 or L sub naught, but that rubber band is stretched with a force that increases its length by a factor of x. So this is how much the string is, the rubber band, I'm sorry, is increased in length by the force F. That force is given by, and I'll call it F of, oh, it's a function of x, so matter of fact, maybe I'll just show that over here, which is equal to a constant times L naught minus x over L naught minus L naught squared over L naught plus x, that quantity squared, like that. What we're looking for then is the amount of work it takes to stretch that by that force. And what we're going to need is the integral from 0 to x of f of x dx. That's the sum of all the work it takes to stretch it from 0 to x. So we have to do this integral. And that integral is best done by breaking it up into the sum of integrals. It's an integral of a sum. There's these two obvious sums right here. So let's go ahead and break it up now and write it as the integral of f naught L naught minus x over L naught, okay, minus the integral of the second part right here, which is L naught squared, L naught plus x squared dx. Okay, and that'll go from 0 to x. Those integrals go from 0 to x. Well, we can break up this one also into a sum of two integrals. So if we break this up, we end up with three terms. The integral from 0 to x of, see, here's f L naught over L naught, so that's f naught times dx, and then minus the integral of f over L naught, f naught over L naught times x dx. And then minus this integral we have up here, 0 to x of f naught. There should be an f naught there, sorry about that. F naught L naught squared over L naught plus x squared dx. Now we could factor out all those constants. So why don't we go ahead and do that now? So this is f naught, the integral from 0 to x of dx, okay, minus f naught over L naught the integral of x dx, and these are from 0 to x, and then minus f naught L naught squared, the integral from 0 to x of dx over L naught plus x, that quantity squared, okay? Now, each one of these are fairly easy to do. This right here is just the integral of x, see? So if you do that integral, that's just equal to f naught times x. Now, that's evaluated from 0 to x minus, here's f naught over L naught, and then the integral of x is 1/2 x squared from 0 to x. Now this next integral, I'm going to try to drop down here just a little bit to work that in. That's going to be f naught L naught squared. And this integral you can look up. As a matter of fact, I think I got some integral tables here. Right here. This is of this form right down here. See, this is a plus bx, that quantity squared, okay, under dx. And in our case, b is 1 and a is L naught. So there's the integral right there. You pick up a minus sign, okay. And when you do that, that cancels this minus sign right here. So this becomes f naught L naught squared over, or times, 1 over L naught plus x, like that. And then that has to be evaluated from 0 to x. When you do that, you pretty much see that at 0, this is 0. So this is going to be f naught x. Okay, minus at 0, this term is 0. So at x, that's minus 1/2 f naught over L naught x squared. Now, plus this term right here. Now, at x equals, at x, this is the same term here, but at 0, x goes to 0, this L cancels that, and so you're left with an f naught L naught right here, which you're going to have to subtract off, okay? So whenever you add up all those terms, then the work will be equal to, I'm going to factor, each one of these has an f naught in it, so I'm going to factor that out, f naught. And then x minus x squared over 2 L naught plus L naught squared over L naught plus x. And then this term right here, when I factor the L naught off, that L naught squared is cancels one of those, so that just leaves minus L naught like that. And so there's the work it takes to stretch that rubber band.